Okay, good morning, you guys. This is a calculator active problem. So it is the year 2006 free response question 2. So remember that the calculator active ones typically are the first two problems that we have for each set of 6 free responses. So that means like you're going to use your calculator. You're going to get points for setup and you're going to get points for answer. You're not doing any kind of derivatives typically by hand or integration by hand. Doing a lot of stuff on the calculator. So reading through the stem of this problem, it says, at an intersection in Thomasville, Oregon, cars turn left at a rate L of t equals 60 times the square root of t times sine squared of t over 3 cars per hour over the time interval 0 is less than or equal to t, which is less than or equal to 18 hours. So this is something that I've noticed when you guys have been doing other multiple choice questions, because it says it's a rate. It says cars per hour. This is a derivative. It doesn't have to have the prime on there to be understood as a derivative. You have to understand the context. So this is a rate of change. This is a rule for the derivative. Okay, it's just marked as L of t. And it says the graph of L of t is shown. And I redrew the graph to the best of my ability that you guys are seeing on your paper. So if this is the graph of L of t, this is the derivative graph. This is the graph of the cars turning left, cars per hour, the rate of the cars turning left in cars per hour over 0 to 18 hours. So of course, the first thing that we probably want to do is we want to probably put our L of t in y1. And I'm going to mark that so that I remember that that's where I'm storing that derivative rule. Okay? It's a little messy to get it into the calculator because you have to make sure you're in radian mode. You have to make sure that you do your own parentheses since we have a trig function squared. Remember that means the whole sine of t over 3. I had Mr. Herney put the t over 3 in pretty print so it's up and down vertically, but the whole thing has to be squared at the end. So you have to have extra parentheses. So this is the shorthand way we can write it on our paper. And remember the x's are t's on our calculator. Okay? So part A says to the nearest whole number, find the total number of cars turning left at the intersection over the time interval 0 to 18 hours. Oh, okay, so if I know this is the rate, cars per hour, and I want to know the cars that turn left, I want to get rid of hours. If I have a rate of change, don't I integrate to get back to the regular linear units? So we're going to set up from 0 to 18, and since they've defined this for us as L of t, you don't have to rewrite this whole thing, just write L of t that you're integrating with respect to time. If we integrate cars per hour, wouldn't we just get back to cars? That's all we got to do. We're just going to math 9 that on our calculator. It does say to round to the nearest number because you're thinking about cars, and so it's like something that you're not going to have a portion of. And you should get, when you're done, approximately 1,658 cars turning left on our interval 0 to 18 hours. Okay? And I think Mr. Herney just showed you that on the home screen. So that was pretty straightforward, pretty easy peasy. But you do have to understand that this is the rate of change and you're integrating. That's like the main big hook right there. So part B says, traffic engineers will consider turn restrictions when L of t is greater than or equal to 150 cars per hour. Find all values of t, so find all your times, for which L of t is going to be greater than or equal to 150, and compute the average value of L over this time interval. Indicate units of measure. So since they're particularly asking us about units of measure, that's going to be points. Up here, they didn't ask, so if you didn't say this were the number of cars turning left, you could still get the points. I would try to put units, no matter if they ask or not, because it just makes you stronger at it. But if they ask, you gotta have units. So one thing that we haven't done a whole lot of yet, probably that I can remember on our free responses, is when it says compute the average value. Do you guys remember that that's fave? So the formula for fave, the function's average value equals 1 over b minus a times the definite integral from a to b of whatever rule you're doing, right? F of x dx, f prime of x dx. It just depends on how it's labeled. But that's kind of something we have memorized for fave. And remember, whatever the units are for this part will be your units for fave. because yeah, you're integrating whatever rate of change here, whatever linear measurement with probably respect to time, but then you go back and divide it by time. So you get right back to the same units as whatever this part is for the function's average value. So this is a lot of context on this problem. It's like it's intense, this problem is. So if you want to know about the turn restrictions when L of t is greater than or equal to 150 cars per hour, what I think about is, well, let's at least figure out first where L of t, find the times, is going to equal 150. So I already know that this is stored in y1. So I'm going to put 150, which is just going to be my horizontal line at y equals 150. And Mr. Herney can show you the graph and show you the window that we used, but why not use the window that they've already used?
So here's going to be the window that they basically already gave you. So you type that in.
So they have every 3 marked, but they're really going by ones. 0 to 18 going by ones.
Okay, there's my y1 and y2. So y2 I've got to 150 now. And I go ahead and graph it, and we should get a graph that looks something like this.
So I have that drawn in, and I'll show you guys what I got. So this first time that I got, and I went ahead and defined it as A, was 12.42831. And again, we want to keep all those digits so we don't introduce any kind of rounding error. And the second time, right where we equal 150 with our L of t rate of change graph, I got for B equaling 16.121657. Sometimes I think if you have a color calculator, it rounds slightly differently. So if your digits are a little bit less than this, that's still going to be fine because it's going to hold enough that your final answer would be correct to 3 places. So those are my 2 times. So kind of rereading. You have to read this one a lot. It does say find all values of t for which L of t is greater than or equal to 150. So that's one of the answers we need. Well, you guys, can't you tell from the graph? Oh, if this is exactly where it's 150, but I want to know where it's greater than or equal to 150, don't I want any of the times in between those 2? Correct? But including those 2. So L of t is going to be greater than or equal to 150 cars per hour on the times, or on the time interval maybe, in between, and since I labeled them as A to B, I'm going to say A to B with closed brackets, hours. So here's my first part. The second part was the fav part. And then, compute the average value of L over this time interval. So since I already have my fav formula in general, I want to compute the function's average value. I can still use A and B, which is kind of why I picked those letters, because I've defined them up here. As long as you define them for the reader, then they will take those variables. You'll have to type them when you type it on your calculator with all of the digits, but you can write them. Of the definite integral, A is our lower boundary, B is our upper boundary, right? A is our lower time, B is our upper time. And then we can't put f of x there because the rule that we're really going to integrate is going to be L of t with respect to time. So we're going to write that down because we're telling them in calculus notation what we're doing. And then Herney's going to show you how that's going to look on the home screen. And what I got, and they didn't say to round here to the nearest anything because this is the cars per hour, is 199.426. So as we are doing this remote learning, and I know it's way harder, if we were in class, I would tell you to do this, seeing you face to face, is as we're going through these, you need to make a list of things that are important for AP. One of those things on the list should be, for fav, the units match the units of this guy. Oh yeah, when I integrate cars per hour, I would get back to cars, but then I'm multiplying by 1 over the time, so I'm right back to cars per hour, because those hours are in the denominator. And since they asked for units of measure, you have to say that.
Hey guys, making a sheet this year is going to be more important than ever because you do get to use, this is open notes for your test. So your calculator should look something like this.
So it's kind of messy with the fav part and all those
with
digits.
all those decimals in there.
And then our L of t we stored in y1. And then we're gonna hit enter and let it think and run it for us. But there's the 199.426. So you only want to round other than the third decimal place if they specifically ask. Otherwise, it's got to be to the third decimal place to get the points. So actually, speaking of points, I'm going to show you what the points are for A and B before we go on to C, which might blow your mind, right? So, all right, so part A is for this problem, 1 point for the setup. So that would be, I think, the whole integral. So you have to have the boundaries correct, I think, on this one. And the LFT is what you're integrating. And then 1 point for your answer. So the 1,658. And since they didn't really ask you for units on that one, if you didn't say cars turning left from the time 0 to 18, if you just had the value 1658, you're going to get the points. For part B, you get 1 point that you explained where the interval would be, where the turn restriction would happen, where L of t is greater than or equal to 150, so that you found the intersection points in like you explained that in words. So this is for your interval. Then you would get 1 point for the average value integral. So did you know that you were going to have to integrate from that lower boundary, I defined it as A, whatever letters you want to pick, to the upper boundary, I defined that as B. The integral means you had to know the boundaries and know it was integrating L of t dt. And then 1 point is with your answer with units. So the reason that they only get that second point for this part is because if you forget to do the multiplying of 1 over b minus a, that's on the answer anyway. If you did not put cars per hour, you would lose it, even if this was right. If it says answer with units, you have to have the units. So we've used 5 of our total of 9 points, which means C is 4, which is kind of hefty. That last problem, Mr. Herney did a video of part A and B and C were all equal, and this one they're not all equal.
I just want to spend another minute here on finding our units, guys. So when you integrate f of x dx, I guess f of x is supposed to be L of t here. Okay, the units for L of t were cars per hour, right? So when we integrate cars per hour, that turns into cars. Okay, but now we have this out in front, which is 1 over b minus a. b minus a, these are times. So we're really multiplying by 1 over time, which in this one is 1 over hours. So now we have 1 over hours times cars, which is cars per hour.
Okay, so part C says, traffic engineers will install a signal if there is any 2-hour time interval during which the product of the total number of cars turning left and the total number of oncoming cars traveling straight through the intersection is greater than 200,000. So before I even read any more, you're like, wait, what? So they are expecting you to be able to turn some English into math. So rereading, they're going to install this traffic signal if for any period of 2 hours, the product, doesn't product mean to multiply, of the total number of cars turning left, I'm multiplying that with the total number of oncoming cars going straight through, is greater than, not greater than or equal to, just greater than 200,000. I'm at the end of the board, so I'm kind of writing all sorts of wonky. Okay, now I'm going to continue. So I kind of turned my English into my math and used a bunch of stuff in words. There is more than one way to solve this problem. I've found from doing this problem year after year, this is the most efficient way that most kids can understand. So this is the way I'm going to teach it. And it says on the next sentence, in every 2-hour time interval, so it doesn't matter what 2 hours between 0 and 18, any 2-hour time interval we pick, 500 oncoming cars traveling straight through the intersection. Oh, so the cars that are going straight through in any 2-hour time interval is always 500. We don't know maybe the total number of cars turning left, but we still know that we want their product if there has to be a signal for a traffic signal to actually be built. Does this end up being greater than 200,000? Well, even though this is all crazy and I've written all this stuff out in words. It's an inequality, and I have a product, I have multiplication. So let's isolate the part we're looking for. Don't we undo multiplication with division? So let's divide both sides by 500. So that means I really want to figure out where the total number of cars turning left is going to be greater than, and it's calculator active, so it's bigger numbers, but when you divide 200,000 by 500, you get 400. Oh, that's what I'm really looking for. Where the total number of cars turning left is going to be greater than 400. So going back to the graph, because a graph is not the graph of the cars turning left. It's a graph of the rate of change of the cars that are turning left, right? It's the derivative graph, which we wrote up here. So I'm going to go back and I'm going to erase this a little bit. And I'm just going to kind of focus for a second on this graph and think, okay, if I want to know cars turning left, just cars, that would be integrating. Oh, if I have a graph, integrating is finding the accumulation of the area under the derivative graph. If I accumulate the cars per hour over a certain number of hours, when I just get cars, and I want to know where it's greater than 400. And I know it's got to be 2-hour time intervals. So I want like a base of 2. If my base is going to be 2, because that's the change of x, 2 times what will give you 400? Oh, wouldn't 2 times 200 give you 400? So I would want like the height, I don't know, to be 200. So if I go just to kind of see, oh, it looks like, even though this is like kind of a crap graph, if I took this 2-hour chunk from 13 to 15, that would be a base of 2. My height is 200-ish, and maybe that would give me something that would equal 400 or possibly be greater than 400 or possibly be less than 400, but at least it's something to analyze. And there's other spots you could go to. You just have to stay within 2 hours. You could probably do 12 to 14. You could probably do 14 to 16. Any of those 2-hour chunks look like this spot would be a height that would be bigger if you thought about like accumulating rectangles than 200. So you just got to choose one and go with it. So I'm going to try the definite integral from 13 to 15 of L of t dt. So remember, you can't have calculator syntax. So even though we store this in Y1, you got to write L of t on your paper. But when you type it in and you math theta on your home screen, you're going to type it in as Y1. So Mr. Harney, can you tell me what that gives you once you run it?
431.931.
Well, that looks like a 2-hour time interval where the cars turning left is greater than 400. So wouldn't that mean that we've proven that we need to have a traffic signal? So now we got to say that to the AP readers. So I'm just going to tilt this down a little bit because I'm getting towards the bottom of the board. So I would say, therefore, yes, this intersection would require a traffic signal because on my open interval from 13 to 15 hours makes a product greater than the 200,000. Okay? So the points on part C, remember we had 4 to work with, went like this. The first one is that you got down to where you understood that you had to consider the cars turning left being greater than the 400. They're going to be pretty loose with that if they can kind of follow your thought process. I did it very like kind of words in inequality. So that's the first point of the 4. The second point is that you have some valid spot that you've accumulated the area under the curve and showed some valid 2-hour chunk. So I'm going to say some valid 2-hour interval. I did 13 to 15. Like I said, I think 12 to 14 works. I think 14 to 16 works. You could like do some stuff with halves, but why would you do that? I would pick whole number hours. And then you get a point for getting an answer that's bigger than 400 in whatever 2-hour window you chose. And then the final point is your answer of yes, but you have to have explanation. So I'm going to say answer with explanation. So then like you kind of like restated the question. Like, yes, there's a traffic signal that's needed, and it's because in this 2-hour chunk of time that our product would be greater than 200,000, or the cars turning left would be greater than 400, which would make the product be greater than 200,000. So this is one that we typically do because it's not the easiest one to like wrap your head around, and it reviews a lot of things we haven't reviewed for a bit. Fave is one of them, the calculator stuff, and this is just kind of wild card craziness, right? Mr. Herney, anything last minute?
Nope.
Okay.
Looks good.
Definitely draw all over the graph that's provided, right? That's why it's best if you can print out the problems so you can draw on the picture of the graph provided.